All right, let's talk about computers. You've got the one on your desk, maybe the one in your pocket. But then there's this other thing you keep hearing about, quantum computing. So what's the real difference? Is it just a faster version of what we have now? Or something else entirely? That's what we're going to break down today. We have these incredible supercomputers, right? Machines that can just crunch numbers at a speed that's, well, it's hard to even imagine. You'd think that with all that power, no problem would be too tough to solve. But that's not the case. There are certain challenges out there that bring even our fastest machines to a grinding halt. So what's going on? Okay, here's a perfect example. Creating new medicines. It sounds straightforward, but to design a life-saving drug, you have to perfectly predict how a tiny molecule is going to behave inside the incredibly complex system of the human body. The number of variables, the interactions, it's just mind-boggling. It's a type of problem that our current computers, even the super fast ones, just aren't built to handle. They hit a wall. And yeah, that barrier actually has a name. People call it the computing wall. To really get why this wall exists, we need to peel back the curtain and look at how the computers we use every day actually, well, think. It doesn't matter if it's your smartphone or a massive supercomputer in a lab. Deep down, they all work on the same basic principle. And look, it's a brilliant design. It's gotten us this far. But it has a kind of Achilles heel when you throw problems at it that have this massive, sprawling web of complexity. So, to really understand that limitation, we've got to go right back to basics, the absolute fundamental building block of every single thing that happens on your computer. It all boils down to one simple concept. And that concept is the bit. That's it. Every single thing you do, sending a message, watching this, playing a game, it's all just a massive, massive stream of these tiny little guys. It's all just zeros and ones, a binary world. The easiest way to think about a bit, it's just a light switch. It's either on, which is a 1, or it's off, a 0. That's it. There are no other options. No dimming the lights, no in between. And this simple, clear, one-thing-at-a-time approach is what makes classical computers so reliable. But it's also exactly where their limits are. Okay, so now I want you to take that idea of a simple on-off switch and just, for a moment, throw it out the window. We're about to step into a totally different universe, one that runs on the famously weird and wonderful rules of quantum mechanics. And this is where things get, well, a little strange. The quantum version of a bit is called a qubit. But a qubit isn't a light switch. A much better analogy is a spinning coin. Think about it. While that coin is in the air, spinning around, is it heads or tails? It's neither, and it's kind of both at the same time. This bizarre state has a name. It's called superposition. It's the qubit's superpower. It can hold the value of a 0, a 1, and, sort of, everything in between, all at once. It's only when you stop and measure it, when the coin finally lands on the table, that it chooses to be either a 0 or a 1. And that ability to exist in multiple states at once, that changes everything. Oh, and if you thought that was weird, hold on. It gets even stranger. There's another quantum trick called entanglement. This is where you can link two qubits together so that they're connected no matter how far apart they are. Their fates are intertwined. If you look at one and it lands on 0, you instantly know without even looking that its partner has landed on 1. It's like they're communicating faster than light. And this creates this incredibly complex, powerful web for doing calculations. So what happens when you take these two wild concepts, superposition and entanglement, and you build a computer out of them? Well, you don't just get a faster computer. You get an entirely new kind of computer, a whole new class of power. Let's just break this down side by side. Classical computers, they use bits. Definite. It's a 0 or it's a 1. Simple. Quantum computers, they use qubits, which are probabilistic. They can be 0, 1, or a mix of both. And this difference is what unlocks something called massive parallelism. It lets them tackle these very specific, hairy problems that classical computers just can't. Okay, but what does that mean in practice? Here's the payoff. Imagine you're trying to solve a maze. A classical computer would try one path, hit a dead end, go back, and try another, one by one by one. A quantum computer, because of superposition, it can explore every single possible path through the maze at the exact same time. It's not about being faster, it's about exploring everything at once. And this isn't just some abstract science fiction idea. This incredible power has real-world applications. So let's circle back to that problem we started with, the drug discovery, and see what this all means. Right. Remember that impossible molecule simulation? Well, with a quantum computer, you can basically map that complex molecule onto a system of qubits. And then you let superposition do its magic. It can explore every single possible way that molecule could interact all at the same time. A problem that would take our best supercomputers literally centuries to solve. A quantum computer could potentially knock it out in minutes. That's the leap we're talking about. And it's not just medicine. The potential impact is huge across the board. We're talking about things like cryptography, where it could break the encryption we use today to protect everything online. But it could also help us create brand new unbreakable codes. It could revolutionize financial modeling, optimize global logistics down to the last truck, and give a serious turbo boost to the development of artificial intelligence. Okay, so when you hear about all this game-changing potential, there's one really big question that pops into pretty much everyone's mind. Is this thing going to replace my laptop? Should I be saving up for a quantum MacBook? And the answer, which might surprise you, is no. Almost certainly not. That's not what they're for. Here's the best way to think about it. Your laptop or your phone, that's like a family car. It's versatile, it's reliable, it's perfect for all your day-to-day stuff. Driving to work, getting groceries, you name it. A quantum computer, that's a Formula One race car. It is an absolute beast of engineering, designed to do one very specific thing at an incredible speed. But you wouldn't take it to go pick up milk, right? They're just different tools for different jobs. So let's wrap this up with the key things to remember. Classical computers use bits, on or off, 0 or 1. That's the rule. Quantum computers use qubits, which can be 0, 1, or both at the same time, thanks to superposition. That's their superpower. And this superpower makes them amazing at solving very specific, super complex problems. They're a powerful, specialized tool for the future, not a replacement for the computer you're probably using right now. But this all leaves us with one last, pretty big thought to chew on. We mentioned that this power could shatter the encryption that keeps all our digital lives safe, our banking, our messages, everything. So as this quantum technology gets more and more powerful, there's a huge, urgent race happening right now to build a new kind of security, one that's quantum-proof. It really makes you think, doesn't it? How do we build a safe future when the very rules of computing are being rewritten?